understand about the evolution of our eyes. The majority of life on our planet depends on the sun for energy. Because life is so tightly linked to the sun, many organisms have evolved the ability to detect and respond to light. Plants turn their leaves toward the sun. Single-celled algae, protists, and other microbes swim toward or away from light. But it is the animals, with image-forming eyes, that have taken light detection to the next level. A predator who can see its prey from a distance, or a prey animal that can see the shadow of a predator approaching, has a clear survival advantage over those who can't. Even a slight improvement in image quality provides a significant survival advantage, allowing for the step-by-step evolution of increasingly complex eyes. The most basic structure, that is widely accepted as an eye, has just two cells, a photoreceptor, that detects light, and a pigment cell, that provides shading and sensing the direction of light. The photoreceptor connects to ciliated cells, which engage to move the animal in response to light. Euglena, a single-celled organism, just has a little eye spot at the head end of the cell. That eye spot is sensitive to light. It can't form an image or see anything. All it can detect is whether it's light or dark. So, that could be the first step. Next, imagine that you have a flat sheet of cells, each of which is sensitive to light. Now, what will happen if you gradually curve that flat sheet of cells? An eye with more photoreceptors can detect variations in light intensity across its surface. But with curved shape, it can also detect the direction of falling light, and hence, the movement of nearby objects. This might have helped in detecting the direction of a predator's shadow passing over. This gives a huge evolutionary advantage over animals with just a flat eye. Now, how did eyes start forming images? Imagine that over time, what is a cup, grows deeper and deeper to close up its open end, making structure like a pinhole camera. But, a pinhole camera does not actually show you much of an image, but it does show you a crude image. The image is blurry and upside down, but you can still see it. We can even find this stage of evolution in today's animals. This is a photo of mollusk Nautilus, an octopus, that has a pinhole camera-like eye. Now, coming to the next part, how did we get a detailed image from an inverted blurry image? The solution to this is a lens. To get a really good image, we need a curved lens. But, how to get that in nature? Interestingly, any transparent curved object can act as a lens, for example, a simple water droplet, or some sort of transparent jelly-like material. Now if this jelly hardens, it will form a proper lens, which can transmit a brighter and clearer image. Sea snails have a blob of jelly that acts as a very simple lens. So, they can focus on an object, even if that image is a bit blurry. Further improvements include evolved pupils that opened and closed to let in just the right amount of light for forming clear images. Muscles evolved to fine-tune focusing and to point the eye in different directions. Photoreceptors increased in number, providing more detailed images. Neurons evolved that could process signals and coordinate behavior. Visual cortex in our brains evolved to process more sharper and colorful images. Starting with the flat, light-sensitive patch, researchers gradually made over 1,800 tiny improvements, forming a cup, constricting the opening, adding a lens, until they had a complex, image-forming eye. It is important to note that every tiny change these researchers made measurably improved image quality. The researchers concluded that these steps could have taken place in about 360,000 generations, or just a few 100,000 years. 550 million years have passed since the formation of the oldest fossil eyes, enough time for complex eyes to have evolved more than 1,500 times. So, that's all about the concept behind the evolution of our eyes.